Today, I want to explain about the structure and evolution of stars. Let me share my screen. We want to talk about neutron stars and pulsars. A neutron star has formed during the supernova explosion if the mass of the collapsing core exceeds the Chandrasekhar limit of 1.4 solar mass. Degenerate neutron pressure counterbalances the gravitation. A neutron star is a dense stellar corpse consisting primarily of closely packed degenerate neutrons. Proposed in 1930s, not verified until 1960. Properties of neutron stars. Diameter of about 20 kilometers, a mass less than 3 solar mass, magnetic field 10 to power 12 times stronger than that of the sun, rotation period of roughly 1 second. Here you see the atmosphere of neutron star, outer crust, then inner crust, outer core, and then inner core. And you see here the magnetic field, beam, and neutron star, axis of rotation. A model of neutron star structure. A neutron star consists of a superfluid, superconductive core surrounded by a superfluid mantle and a thin, brittle crust. There is evidence for an atmosphere. As you see, here crust, superfluid neutrons, and superconductive protons. Here distance from center in kilometer, exotic state of matter. Here is the density. As you see, the density increase as they go to the core, and the distance increase when they go far away from the core. The discovery of pulsars in 1960s. Pulsar is a source of periodic pulses of radio radiation. Pulsars PSR 0329 plus 54. Interval between pulses 0.714 seconds. As you see the time intensity. You see here Jocelyn Bernal. She was a graduate student at the University of Cambridge. She discovered, and she was the first one who discovered the pulsars in 1967. In that time she was a Ph.D. student. And here is her notes. Here is Jocelyn. And but unfortunately, 7 years after that, her supervisor Anthony Hewish, was granted a Nobel Prize in 1974. She was not even mentioned in anything in Nobel Prize or anywhere else. And you see here that the remote observation of a rapidly pulsating radio source. Unusual signals from pulsating radio sources have been recorded at the Mullard Radio Astronomy Observatory in Britain. The radiation seems to come from local objects within the galaxy and may be associated with oscillations of white dwarf or neutron stars. Pulsar found in the Crab Nebula. Crab Nebula was created by the supernova explosion occurred on July 4th in 1054, recorded by Chinese astronomer. A fast rotating pulsar with period of 0.033 seconds or 30 times per second is discovered at the center of Crab Nebula. Such fast spin cannot be from a white dwarf. Here you see the Crab pulsar in visible light, pulsar in on state, and pulsar in off state. But here you see the pulsar, the Crab pulsar in X-ray. Pulsars are rapidly rotating neutron stars. Pulsars are neutron stars, but they are rapidly rotating. A neutron star can spin very fast because of its small size. Magnetic field is strong because all magnetic field in the progenitor star is squeezed and concentrated into the neutron star size. Magnetic axis is inclined to the rotation axis. Charged particles from the surface are accelerated along the intense magnetic field and radiate electromagnetic radiation. And here you see the axis of rotation, radiation beamed along magnetic axis, magnetic field, and we can say pre-main sequence stars also pulsars have accretion disk, also have magnetic field, and we call it Bromstring radiation, which is from magnetic field, and it is related to non-thermal radiation. And in neutron and pulsars stars, there is no fusion, so the flux is low, which is radiated, especially in optically. The only chance is to detect non-thermal Bromstring radiation. Pulsars are beamed radiation sweep the Earth. Because charged particles move along the magnetic field lines, their radiation is also along the magnetic field lines, forming a radiation beam in parallel with the magnetic axis. The beam sweeps around the sky as the star rotates. If the Earth happens to lie in the path of the beam, the pulsar can be detected. Pulsars is like a lighthouse beacon, as you see here. Pulsars is a rotating neutron star whose radiation beam happens to sweep the star. And if we are in the line of the beam, we can detect the beam of the pulsars. Periods of pulsars. Radio telescopes have found more than 1,000 pulsars, and their rotation period is in a wide range from 1 millisecond or 0.001 second to 10 seconds. An isolated pulsar slows down as it ages, so its period increases. And you see here the neutron stars rotating is gradually slowing down, so the pulsar period increases. Pulsar glitch, the neutron star's rotation suddenly speeds up and the period decreases. After the glitch, the neutron star rotates, resumes its slowdown, and the period again increases. What powers the Crab Nebula? The ultimate energy source for the luminous nebula is the spinning of the neutron star. The spinning or rotation energy is transferred into the surrounding nebula, which results in the gradual slowdown of the star. The nebula shines due to the radiation from the energetic electrons accelerated along the magnetic field. And you see here the fast-moving material from the pulsar creates shock waves, forming X-ray emitting rings. This is the Crab pulsar in one light year. And the pulsar's magnetic field films outgoing materials into two opposite direction jets. Pulsars gradually slow down but have glitches. The pulse rate of many pulsars is slowing steadily. The sudden speeds of the pulse rate called glitches may be caused by interactions between the neutron star's crust and its superfluid interior. We can say that pulsars slow down because angular momentum lost by radiation which is going on the beam, and so its period going down. There is a glitch in pulsars or somehow like hiccup, which means they sudden increase or decrease, and mostly decrease. Something is breaking the pulsars. Maybe there is some material falling into the pulsars. Because pulsars still have solar masses, they have a strong magnetic field, so they can still accrete some matter. If the material is falling onto the pulsars, then they will be slowing down, so the period will be increasing and slowing down. Gravity equivalent of curvature of space. The curved space not only acts on the object with mass, the curved space also acts on the light, even though light does not have mass. The light seeks to move across the shortest distance between tau points. In a curved space, the light bends instead of moving in a straight line. You see here, a massive object curves the space-time around us, and you see here, far from the object, space-time is nearly flat. Close to the object, the curvature forms a wall. In Einstein's picture of gravity, other objects sense the curvature and are drawn into the well. Pureful theory of relativity. During the solar eclipse, the starlight is deflected by the sun's gravity by an amount of 1.75 arcsecond in 1919. Mercury, the closest planet to the sun, shows an excessive precession that perfectly fits the slightly curved space near the sun. If you can say this is Earth, Sun, and a ray of starlight is deflected by the sun's gravity, and then because of the deflection, the star appears to be here, but the actual position of the star is here, and they have 1.75 arcsecond distance. Here you see the line axis of Mercury's orbit slowly changes orientation or shown greatly exaggerated. Gravitational redshift. Because of the time dilation, the period of light wave from the surface of a strong gravity becomes longer, and thus the frequency becomes smaller. Or equivalently, wavelength becomes longer. This is so-called gravitational redshift. And on the surface of a white dwarf, redshift, the delta lambda over lambda is a factor of 10 to the power minus 4. On the sun, the gravitational redshift is negligible. Theory of relativity predicts black holes. In a supergiant star has relatively weak gravity, so emitted photons travel in essentially straight lines. In here, as the star collapses into a neutron star, the surface gravity becomes stronger and photons follow curved paths. Continued collapse intensities the surface gravity, and so photons follow paths more sharply curved. When the star shrinks past the critical size, it becomes a black hole. Photons follow paths that curve back into the black hole, so no light escapes. We can say the source of energy for pulsars is the material around it of the supernova explosion, and some of the material is coming back to the pulsars. The radiation is coming from the neutron and proton, which are radiating from the pulsars, so there is still luminosity ongoing. And also radiation is from magnetic field. And also, if the strong force cannot stop the collapse, then we have black holes. And they do not radiate any flux. A stellar black hole, if a stellar corpse has a mass greater than about 2 to 3 solar mass, gravitational compression will overwhelm all forms of internal pressure, including degenerate neutrons and nuclear forces. The stellar corpse will collapse to a singularity immediately around which the escape speed exceeds the speed of light. Far away from the black hole, the space is the same as the case of a normal main sequence star. Here, a black hole sharply curves the space-time around it. Then far from the black hole, space-time is nearly flat. Close to the black hole, the curvature forms a well that is infinitely deep. Objects that venture too close to the black hole cannot escape from the well. Certain binary star systems probably contain black holes. Black holes have been detected using indirect methods. Some binary star systems contain a black hole. In such a system, for example, Cygnus X1, gases captured from the companion star by the black hole emit detectable X-rays. We can say we can detect stellar black holes by in this way. If we have an object which is rotating around it by its orbit and distance, we can calculate what mass goes to the center of the stellar black hole. For example, in binary stars, when one companion is more massive, for example, 5 solar mass, which is more massive than neutron stars, we can say that is a black hole. And we can detect the X-ray of companion, which its mass goes to that. So we have the mass and X-ray of companion. Gas from the supergiant are captured into an accretion disk around the black hole, and we have X-ray, and this is black hole and blue supergiant. As gases spiral toward the black hole, they are heated by friction. Just outside the black hole, they are hot enough to emit X-rays. This is a schematic diagram of Cygnus X1. Evolution of closed binary systems. There are many multiple star systems in the galaxy. For the vast majority, the separation of their stars is large enough that one star doesn't affect the evolution of the others. Here you see, for example, for solar mass and less than solar mass, higher than solar mass. We can say the ratio of binary systems depend on the mass of the stars. For example, stars with 3 solar mass are binary systems that are much, we have many of them, or we can say maybe approximately most of them are in binary stars. For solar mass, around we have around 50% binary systems, and for less than solar mass, there are a few binary systems. So we have more binary systems for stars that are more massive than our suns. For example, 3 solar mass, they are mostly in binary systems. And if we know the orbit and mass of the stars, we can say they will be evolved as single or binary stars. The Algol mystery. Algol is a double-lined eclipse in binary system with a period of about 3 days, very short. The 2 stars are star A, BA, B8, a 3.4 solar mass main sequence stars, and star B, that is G5, with 0.8 solar mass, that is a subgiant star. Something is wrong with this picture, as you see. If it is a 3.4 solar mass, why it didn't leave the main sequence, and it is still in main sequence star. Also here, it is subgiant star, but its mass is 0.8 solar mass. Something seems to be wrong with this picture. The more massive star A should have left the main sequence and start up the red giant branch or RGB before the less massive star B. What is going on here? The key is the short period orbit, and it means that they are so close to each other. Originally, the system contained star A at 1.2 solar mass and star B at 3 solar mass. Between the 2 stars is a point where the gravitational forces of the 2 stars balance. This is called a Lagrangian point. As you see here, for example, it is Sun, it is Earth. And we have Lagrangian 1, 2, 3, 4, and 5. Or we can consider as Earth and Moon. As the star B evolves and expands as it heads up the red giant branch, when its radius equals the distance of the Lagrangian point 1, called the Roche radius. And the material in star B enveloped feels a stronger attraction to star A, and there is mass transfer from B to A. As you see here, Roche surface, inner Lagrangian point L1, orbital plane. In the case of Algol, star B transferred a 2.2 solar mass of material to star B. At first, star A had 1.2 solar mass, and then it became 3.4 solar mass. And star B, it had 3.3 solar mass, and after a while, it became 0.8 solar mass. And you see here the primary eclipse, Algol 1, A and B, and then secondary eclipse, Algol A and Algol B. And you see here, Algol A, it was something like this, and then It was something like this, and then become this, and then again for angle B. Mass transfer binaries. Think about the continued evolution of alcohol, and you have the explanation for nova. For if the original primary transfers most of its mass to the original secondary, you are left with a massive main sequence star and a white dwarf. When the original secondary starts to evolve up the RGB or red giant branch star, it transfers some material back onto the white dwarf. White dwarf reignition in a binary system. A nova is a faint star suddenly brightens by a factor of 10 to the power 4 to 10 to the power 8 over a few days or hours. It reaches a peak luminosity of about 10 to the power 4 solar luminosity. A nova is different from a supernova. Luminosity of 10 to the power 9 solar mass. For supernova, material from an ordinary star in a closed binary can fall onto a surface of a companion white dwarf. Because of a strong gravity, the transferred hydrogen mass is compressed into a dense layer covering the white surface. When the temperature reaches about 10 to the power 7 Kelvin, hydrogen fusion ignites through the surface layer, producing the sudden increase in luminosity. And we can see that supernova has more luminosity than nova. When we have white dwarf and the material of its companion goes to the white dwarf, hydrogen shell around the carbon and oxygen core ignites, and then it explodes a lot of radiation, which we call it nova. Then it stops, and then it accretes the mass again and again. We have nova. And but still it has no fusion. Depends on which shell ignites hydrogen helium. We have different nova. Difference between supernova type 1 and nova is in supernova type 1, white dwarf just has a carbon and oxygen in the core without hydrogen shell, and so core ignites. But in nova, white dwarf has a core and also hydrogen shell, and so hydrogen shell ignites, not the core. But in both, we have white dwarf and its companion. Here you see the nova Perseid became one of the brightest stars in the sky in 1901. There is an expanding shell from the explosion. The velocity of the material is about 2,000 kilometers over a second. Here is a nova Cygni 1992 illuminated a cloud of nearby hydrogen gas. The expanding shell of the nova could be seen a few years later with the Hubble Space Telescope. Nova Cygni in 1994. Most nova are recurrent. Every year there are 20 to 30 novae observed in the Milky Way. Naked eye novae occur more likely one per decade. Here you see the light curves of nova, time, and apparent visual magnitude. We have material from a star accretes onto a companion white dwarf. When enough accreted material builds up, thermonuclear reactions occur on the white dwarf's surface, creating a burst of visible light. And the nova fades over several weeks. Thank you for your attention and see you next time. Bye.